This is our last lecture in this course, lecture number 10. We started the course from discussing how we analyze the source code which programmers write, so how we understand the syntax of the code, how we break it down into symbols, how we break it down into tokens. Then we discussed how we put together those symbols in order to understand the semantic of the code, how to translate these symbols into the meaning of a program. Then we discussed how we can analyze the program after it is written by a programmer, how we can look at it from the perspective of a data flow analysis. And then we discussed the symbolic execution technique, which helps us to simulate the execution of the code and to understand where and when certain values may show up at certain nodes of the control flow graph. And we also, the last of the previous lecture, we discussed the model checking technique, which allows us to do even more complex analysis of the code when simulating the execution and again understanding what are the properties of the code in order to prevent the bugs. To finish this, the last lecture will give us an overview of how machine learning can help us make program analysis even better. And almost in every lecture, especially the previous 3 or 4 lectures, I gave you some little taste of machine learning. I showed you this ChatGPT examples to show you how to demonstrate you how ChatGPT, which is the most powerful right now artificial intelligence instrument, how it can usually and often, not usually, but very often outperform the traditional analysis methods, outperform data flows and flow analysis, outperform symbolic execution, and sometimes even outperform model checking. Today we will try to look at how this machine learning can help us even further. So ChatGPT, it seems to me, is the first very interesting, very powerful step towards a very bright future of which we're expecting in the area of program analysis. So let's see how it will work in the future. And I believe some of you can contribute to this future and make it even more interesting, more comfortable for programmers, because everything we're talking about in this course is about how to make code writing more comfortable for programmers, or how to make the results of this code writing more effective for computers. If you write the code and the compiler is smart enough to rewrite your code before giving it to the computer, then of course the programmer feels more comfortable by writing the code, because eventually the code will be more suitable for the computer. So a long time ago, earlier, when people only started to invent programming, it was a direct connection between how you write the code and how the machine executes the code. Now there are compilers and optimizers which stay between us writing code and machines executing the code. And these compilers, they optimize the code, making it more suitable, making it faster for the machine. So usually very often programmers, even when they write on a system level programming languages like C, C++, Rust, for example, they even don't know exactly what will be given to the computer to run, because these compilers and optimizers, using the techniques which we study at this course, including data flow analysis and including symbolic execution, they just understand how to more effectively present the code to the machine. So all of this is to make the life of programmers easier. So, but before we go into looking at how machine learning can help, let's take a look what is machine learning. And I'm not sure everybody of you understands that, even myself, not an expert in that. I know how it works. I will try to present you now the key elements of that. But that's a separate territory. What is machine learning and how it works? But still, we need to understand what it is before we jump into how it may help us in the analysis of the programs. So what is machine learning? This is actually the structure of this lecture. So first we understand how machine learning works. Then we'll look at so-called AI coding companions, which are different right now. And I will give you half a dozen of examples which exists right now in the market, and which I use personally. So to give you an overview of how machine learning already is helping us in program analysis. And then the final step, we're going to discuss what is next. So what's going to happen in the next 10 years. And that's going to be for you the motivational part of this speech, of this lecture, which may push you forward into this particular area of research. How machine learning works. Let's start from a deterministic algorithms. Let's say we write a program which is supposed to take the current time of the day in the two arguments, hours and minutes, and in return it has to say hello. So it has to return either good morning or good afternoon or good evening or good night. So this algorithm right now, which you're looking at, is but it is deterministic. We know exactly what it returns if the provided input is this or that. And this algorithm is written by a human being. So some programmer, in this particular case it was me, so I wrote this algorithm and I gave this information to the computer in a very deterministic way. So I know exactly what I was programming. I know exactly that if you tell me that it's 6 o'clock, for example, then the answer will be good morning. It's very deterministic. And most of the algorithms, all of the algorithms which we were writing before the era of machine learning and before we touched the machine learning, all algorithms are deterministic. So we, using this branching if then else, we tell the computer which way to go and what is the expected output. Nothing is wrong in this algorithm. It works. However, it is written by a human, it is written by a programmer, and the programmer needs to know upfront what is the right way to say hello. So the programmer tells the computer, gives the computer the knowledge, we can say train the computer, how the computer should behave. And this knowledge is coming from a programmer, not from the world around the computer. The computer is not learning the reality. The computer is being given the reality. The model of reality is coming from a head of a programmer, of me in this case. So I tell the computer exactly what is the world around us. The world behaves like this, and the computer says, all right, I'm gonna repeat it, I'm gonna work in a way which resembles the reality which we know. So we know if it's 6, then it has to be good morning. It's okay, but it is deterministic. Like I said, not everything can be implemented this way. Not every algorithm can be as deterministic. Why? Because for quite complex reaction which we expect from the computer, we cannot really explain to the computer using if then else branching how to behave. And I will give you an example in this particular case. So imagine we want to use machine learning in order to give us the same answer. So let's take a look at this slide. First, let's see the description of what is machine learning. Machine learning is the process, I'm reading the text, the process of training and so-called ML, machine learning, ML model. The process of training such a model involves providing a learning algorithm with the training data. So imagine machine learning model is like a black box which is trying to behaves like the world around it. So when you start it, it's an empty box. It doesn't know how the world around it behaves. And then you start training it. So you provide the information telling that, look, the world behaves, and look at this, and look at the left column with the data. So this is the training data I'm giving to the model. So I'm telling to the model at 8:35, I just observe the reality and I know that the person says good morning. So let's say I'm just looking at a group of people and see how they greet at each other at different time of the day. So I see at 8:35 somebody says good morning. At 8:40 somebody says good morning. At 10 o'clock they say how are you. At 11:55 they say good afternoon. And so on and so forth till the end of the day. So these are the data, which we call the training data, which me, a data scientist, as somebody who is training the model, collect from the real world. And now I want the model to, now I'm using the word model as a verb. So now I want the model to model the world, to start acting in a way which very closely resembles the real reaction of people, the real behavior of the people. And it could be quite difficult to do with the if then else implementation, like we did before. And in this case, I don't want to do it writing the algorithm in a deterministic way. I want this machine learning model to understand how the world behaves, to learn. They say to learn. So the model should learn. This black box becomes not anymore an empty box, but a smart box, which knows, more or less, not exactly, but it sort of knows what is the right way to answer if somebody says, if it's 11:45. So the algorithm finds, like I continue to read the text, the algorithm finds patterns in the training data that map the input data attributes to target attributes, and it outputs an ML model that captures these patterns. So when I train the model, I provide to the training algorithm, I provide an empty model which knows nothing, which is empty box. And then the training algorithm starts providing data into this box, and the box becomes smarter and smarter and smarter. And eventually, the result of this training is, look at the right column, it's the function f, which accepts hours and minutes and returns the G. The capital G is the greeting. So instead of implementing this function myself, using the Java programming language and this constructs like if then else, I just magically build this box, this model, they call it ML model, which apparently starts behaving like a function, which gets hours as an input, and H, capital H, belongs to the set from 0 to 23, and then capital M is a minute, which is a set from 0 to 59, and G is a greeting from one of the four elements. So it's going to be good morning, good afternoon, good evening, or good night. So look at this again from a high-level perspective. So you somehow magically create the box which knows how to answer these questions. You give this two numbers, it returns you the greeting. So how it happens? How can we turn this data on the left into a box, into a model, which will know how to answer our questions? In order to do that, we do a few steps. Actually, this is the major step which data scientists they do. So they call it embedding or the features. So there are two things actually. The title of this slide should be features and embeddings. So first step is that they look at the data and this is the raw data which is coming to us as a training data. So we just get this data from I'm looking at the left column. So this left column shows us the data obtained from the real world. These are the features. So for example, the hour, the numbers 8, 8, 10, 11, and so on. These are the feature number 1, let's say. The feature number 2 is the minute, 35, 40, 00, 55, and so on. This is the second feature. The third feature is the text. The text which we're getting from the user. So we have 3 features here. Feature 1, feature 2, feature 3. Hours, minutes, and the text. These are the features coming to us. Now, these features are not really yet suitable for the training because they're not yet ready to be interpreted by the computer. For example, how are you is something which we are not expecting to anyhow interpret because we're only interested in 4 greetings. Good morning, good afternoon, good evening, good night. And for example, good day is also a value of the feature which we cannot also interpret properly. So we are a little bit lost with these features. So these features are not helpful, are not ready yet enough, are not yet ready for the training, for using in the model. In order to prepare them better and to sort of normalize them, then data scientists, they use embeddings, so-called. So into this structure, into this data set, they call it data set. So into this data set, they embed additional information. So it was 8:30 good morning, and here I just don't show you good morning because there's no space for that. So I show you the thing which we embed. So we embedded here the word morning, and here again the word morning. Here nil. So here we completely destroyed this element from the data set and say we're not going to use it because we don't know how to. Yeah, we don't know how to embed anything here. So we don't know exactly what the person said here. So we delete this element from the data set. The same happened from the good day. We delete it. But in other cases, and look at the evening, for example, we don't delete them. We just somehow, using some method, again, some additional algorithm, we just map from this feature into this new feature, which is called embedding. So how do we transfer that? In this particular case, I did it, let's say, manually. So I just go through this, all of these elements. There are not so many of them. So I manually decided which one means what. For example, good afternoon, sir, I turned into afternoon. Good evening into evening. Just evening, again into evening. So this mapping from the feature to embedding, or from a number of features to maybe a number of embeddings, this is the process, as they call it. And embedding is a relatively low dimensional space into which you can translate high dimensional vectors. So in this case, these dimensions on the left column the dimension is higher because there are actually, I don't know even how many dimensions are here because they're text, and it's not really formalized text. It's just how are you? It's a natural language, piece of natural language text. In this case, we have much lower dimensional vectors. So in this case, there are actually 3 dimensions, 1, 2, 3. This 3-dimension vector, which is finally being transferred into, now I'm looking at the third column, it's transferred into vectors. So these vectors, which you can see on the third column, is the input to a machine, to a model, to the training process of the model. The job of a data scientist is actually to one of the steps which must be performed by a data scientist, to take the features, to take the data set with the features on the left column, and through a number of these embeddings, move to the final vector, to the collection of vectors. And then you give these vectors to the machine and you ask the machine, please train yourself as a function from the first 2 features to the target feature. The target feature is the feature number 3 in our case. So the first 2 elements of the vector are called the input feature, input attributes or input features, and the last one is the target attribute. So now we need to find a relationship. We need the model to start to learn somehow internally. We don't know how exactly it's going to happen inside the model. It could be anything there. It could be neural network, it could be some simple algorithms, it could be something very complex. We don't care right now at this course. We just know that there is a black box which can somehow internally decide that according to the information already received, it will understand that in the future, when somebody will come in, it's going to be 14, for example, hours and 47 minutes, then the answer should be good afternoon. We don't tell the model exactly that. We never tell deterministically that if you find the time which is 14 hours and 47 minutes, then please answer good afternoon. I never said that. But the machine somehow learned that internally. And it built this correlation between the input attributes and the output, the target attribute. That's it about machine learning. Everything else you want to know, it's going to be just a discussion of how complex is the vector, because usually the vector is not of the 3 dimensions. It's going to be vectors with thousands or maybe even millions of these elements. There will be going to be large vectors, and how to build those vectors, that's a separate question. A big question. And then also the big question is, how do you build this black box so that you give those vectors into the black box and the black box becomes smart, maybe potentially as smart as this ChatGPT. So these are the questions the data scientist must answer. So to finish the description of machine learning, here's what data scientists are doing. They're doing actually 5 tasks repeatedly. Repeatedly means that they do 1, 2, 3, 4, 5, and again 1, 2, 3, 4, 5, 1, 2, 3. So they make those circles until they get the really good smart model, as smart as ChatGPT, for example. So this is exactly probably how, I don't know exactly how they built ChatGPT, but probably they were doing something like that. So first step, they collect and clean the data set. By cleaning, it means that they remove the elements which are not really suitable for the training, like we did. You saw before, when somebody said, how are you, instead of saying good morning or good evening, we just remove that from the data set because it's the information which is not helping us, but only it's just a noise in the data set. So we need to collect the data set somehow and clean it up. That's the first step. So how you do it, you go to the real world, you maybe collect it from real people. Like in our example, we probably were listening to the conversations of the real people in order to build a model, a machine learning model, which copy the behavior of people. So collecting the data is difficult, and in the case of a program analysis, which we're going to discuss a bit later, then the data set is usually the sources of the source code. So the large amount of source code samples, where you have the Java code, thousands of millions of lines of Java code. So you somehow collect it into some large data set. And for example, you create a data set of, let's say, Java classes. So class number 1, class number 2, class number 1 million, class number 1 billion. So it's a huge data set of classes. So let's say you build a model which will look at the class and will say, this class is designed good and this class is designed bad. So let's say you're trying to build that kind of a model, which will non-deterministically decide by looking at the class on the source code of the Java class, which decide whether the design is great or design is average or design is poor. To do that, you need to collect a data set and probably in the first approximation, your data set will contain 2 attributes or 2 features. The first one is the source of the Java class, and the second one is an opinion of a human being. And the human being says the class is good or not good, the class is good and not good. So you will have 2 columns collected somehow from real programmers. And then you feed those, somehow you do the embedding, of course, because you cannot just take that and put it to the model. You need to move from here to the vectors, but then you train the model with this information, and then you can come to the model with a new class, which the model never saw before, and ask, what do you think about this class? And the machine and the model, if you did the other 4 steps properly, then it will tell you the design is good or it's bad. So you collect it and clean it up. Second, you define features plus embedding. So like I said, you look at the data set and then you define what could be the features. What are the columns of this spreadsheet of data? So in our example, which we had 3 columns. The first one is hour, and then the second one is minute. The third one is the greeting. It's pretty simple. In real applications, there are much more features. There are hundreds, thousands, sometimes even millions. Well, I haven't seen millions, but there could be. So usually there are many more than just the 3 of them. And plus embedding. So embeddings, you think how you can manipulate with the features and modify them and derive some new features, some new attributes, and embed them into your data set. That's the next step. So you don't just look at the data set, you make it larger. The step number 3, you choose and tune the algorithm. So you decide which one is going to be the training algorithm, which will take the input data and create the model. So you basically choose the model, not just an algorithm, but you decide what's going to be in this black box, how it's going to work. And there are many existing algorithms. You can invent your own algorithm, but usually people just take an existing one, which was already created by somebody, which was tested on some data sets, and they just take it and use it. And they tune. The tuning means that they configure the parameters of the algorithm. So the algorithm by itself, which is taking the data set and training the model and building the model, it has definitely a lot of parameters inside. So it may be, again, I'm not going to dive into that, but just understand that the algorithm definitely it's not exactly the same for all possible data sets. So for your particular case, you take an algorithm, change it a little bit, and see how it behaves. See how it behaves? These are the next two steps. The step number 4, you train the model. Finally, you take the data set, you have the algorithm, you define the features, so you have the vectors. You derive the vectors from the data. And then you take those vectors and you have already the algorithm, you push those vectors into the algorithm, and the algorithm just collect the data, train the model, and make the model more and more and more smarter. And that takes time. This is where these GPUs are being used. This is where the computing power at the step number 4 is actually consumed. Most of the power is consumed here. So when they tell you that, let's say, ChatGPT was trained on the billions of data, on the billions of data items as an input, and it took them 2-3 months. So you understand that 2-3 months were spent on the step number 4. So they were giving these data, these billions and billions of vectors, to some large model. Large means a complex algorithm, and they were doing it using many servers, many GPU. They use GPU for that because of the nature of these algorithms. So they need massive vector and matrix operations inside. So that's why they use GPU. And this GPU power is being consumed at the step number 4. A lot of power. The larger the data set, the more time it will take to train the model. The more complex is the algorithm, which we decided to choose at step number 3, the longer it will take to train the model. And finally, you validate the model. What do you mean validate? You just give the model some data which the model hasn't seen before. So you train, like in our example, you train the model with the greetings provided by the people, which we observed from the reality. But then when the model says, okay, I'm ready, and the training is finished, then you ask the model, okay, what would you be the greeting if the time would be this? And you give the time which the model hasn't seen before. And the model makes a guess. It says, in this case, I would say good morning. And this is where the magic gets born. So the model hasn't seen this information before, but it creates the information. And that's what we call artificial intelligence. So we say this is artificially created intelligence. We didn't configure it there. We didn't explicitly set to the model what to answer, but the model suddenly says, hey, I know. And the answer comes from the machine, and then we get surprised and we call it artificial intelligence. And you validated the answer. So you look at the answers and you see, hey, the model actually gives artificial intelligence, which is wrong. So the model is answering me good morning while it's an evening, for example. So then you get back. Then you make the next circle, the next cycle of this, the next iteration. So you go to the step number 1. You look at the data and say, hey, maybe I provided some wrong data to the model. Maybe somehow I didn't clean it up properly. And somewhere in my data, actually, there is an answer which says good morning while it's actually afternoon. So you clean up the data again. Then you define the features. Maybe you made a mistake here defining the features. Then you choose maybe a different algorithm. Maybe you failed to train the model properly, so you retrain it again, and you do the validation again. And you see, okay, let's see how it behaves on this data one more time. And if the accuracy, the precision is higher, if the amount of wrong answers is smaller comparing to the number of right answers, then you become happy and maybe you stop here, or maybe you do another cycle to see how can even more improve the results. That's it. This is machine learning, this is data science. I'm sure that you were told that at some other courses, but still you need to understand that. So now let's get to a more interesting discussion, how this whole thing can help us write code better. And I will give you a number of examples, practical examples, of AI so-called coding companions. And this name is coming from Amazon, actually. That's where I found it. So Amazon is calling them AI coding companions. So these are the models which are trained by somebody, and they become so smart that they can give us some suggestions, improvements, so they can code with us. They can sit next to us and maybe help us a little bit. Just like compilers. Again, I'm just connecting this topic with the rest of the course, which we already passed through. So this is exactly the same job as, for example, compilers are doing, and the code analysis instruments were doing before, static analyzers, but these companions are more powerful and less deterministic. So if the compiler with a data flow analysis algorithm inside was quite deterministic, even though it was making mistakes, like you know, it was giving false positives as well, it was giving false negatives and all that that kind of mistakes, but still it was deterministic. So you provide the same input, it will give you the same mistakes, it will give you the same numbers, the same answers. Here we're talking about these coding companions, which unpredictably behave in most cases because they are AI driven, because there are models inside which were trained on millions of data input vectors, and nobody knows what's inside their black boxes. Nobody knows how this machine learning model, which their creators created, and how these models work, we don't know. They just work. They just provide the output. But we cannot get into it and say, hey, on the line 75, the decision was made wrong, so let's a little bit fix it. No, this is one of the strongest parts of the machine learning business, and one of the weakest parts at the same time, is that the machine learning model is actually a black box, which nobody can decompose in most cases, unless it's a really primitive algorithm there and very small amount of these attributes on the vectors. But if there is something bigger than just a few, then it's impossible or close to impossible, but usually it's impossible to understand why the decisions are made. They just made. And if the decisions are wrong, like I told you, you just go again, make another cycle of retraining, but you cannot really fine-tune and debug the model by changing a little bit of if then else instructions in there. So I'm giving you a number of examples. Example number one, the most canonic, the most classic, is auto-completion, so-called. Auto-completion, probably most of you have heard about Copilot. Copilot, made by GitHub, is actually suggesting code completion. When you type the code, when you type your program, then it just looks at your program and it suggests you immediately how to continue your coding, which may be quite helpful. I can probably explain you how it works internally. So it just looks at the code which is already written before. It just understands the code which stays before the cursor and after the cursor, so it's the context. So it looks at everything around your place under the cursor, and then it just asks the model, what do you think would be the most relevant piece of code to be inserted into this position at the cursor? And the model, which was trained by looking at millions of other pieces of code of Java or C# or whatever, Python code, depending on the language you work with, then the model just makes a suggestion. And I will show you right now how it suggests. It's a funny example. So we designed our own programming language in the group which I work with right now. So our programming language is, look at this example. So this is a piece of code in our own programming language, which is on GitHub definitely, but I'm sure that this model, the Copilot, didn't see a lot of code samples on this language. I think so, because the language is not popular as Java. It's absolutely not popular. It's our own. And you can see the syntax of this language. It's very unusual. So it doesn't look like Java. It doesn't look like Python. It looks very different. I'm not sure you can even understand what the code on this picture is doing. But when I give this code to Copilot, then I remove, look at this, line 68. So look at this. I remove the cursor at the line 68, and I wait for half a second, and then the Copilot suggests me. This is the gray area under the number 1. It was suggested by Copilot. It did it wrong. It suggested me a complete garbage. So this code is not going to work. This code is not even syntactically correct, because in our language you cannot say this line, look at the line 87, so you say XY, this is correct, and then the greater sign, and then plus. So plus is illegal here, syntactically. So it got the syntax somehow wrong, but overall it got it more right than wrong, I would say. So you have to understand how this code completion works. It doesn't understand the semantic of the code. It doesn't understand the syntax of the code. it just looks at the code as words and spaces and numbers and just a collection of like a natural language, I would say, like something that people are talking, just a natural language. And then I removed another piece of code and also asked it to give me a suggestion. So I removed another line and it gives me something else, which is now in this case syntactically correct. But again, semantically, it's a complete garbage. So it tries to, another example, it tries to complete my code by helping me with these suggestions, even not understanding the language, not understanding the syntax, not understanding the grammar rules of the language. It just, by looking at the words there, it tries to complete the sentence. So for this model, for this language, it's called, this behind this Copilot, as far as I understand, there stays so-called large language model, which treats the source code as a chain of words and spaces and new line characters, and that. And in our particular language, in our programming language, experimental one, it's not helpful at all, because it suggests the total garbage. But in case of Rust, for example, which I code right now, and in case of Java, which I also use right now, it sometimes suggests pretty accurate code completion pieces. Quever, I have to tell you that my personal feeling is that still this technology is quite, in my opinion, has quite limited limited possibility of being immediately useful by practical programmers, because the amount of errors, the amount of wrong code completion suggestions it gives to us is still quite high. It's very high in my personal experience as a programmer. It gives me many recommendations, and it gives them immediately. It's not like I need to go somewhere in the IDE and click the button and say, please suggest me what should I type next. It immediately suggests me. Actually, code completion was there before artificial intelligence, before Copilot. You know about that. So code completion is the feature in many IDEs and many integrated development environments, which existed, I don't know, 15 years ago, 20 years ago, when you type something and there is only one option to continue, or maybe a number of options to continue from this point. Then the IDE just suggests you that this, for example, you say just call a method on an object. So you say, this is my object X, and then you say dot and start typing. X dot hello, for example. And there's only one method hello in the object X. So the minute you say H, starting to type hello, then the IDE will suggest you ELLO. So these letters, they will just show up, because it's very deterministic. It's just deterministic, not very, but it's pure, simple, deterministic algorithm. It just goes to the source code of the object X. It finds all the possible methods. It understands that there's only one possible one, which starts with the H, and it gives you the list of, it gives me just one suggestion. It was there before. But Copilot introduced the next level of code completion. Not just completing the name of the method, completing the piece of code, the large piece, a number of lines, a few lines, maybe the entire algorithm. And it works, but again, in my opinion, the quality is still very, very low. It's so low that in most cases it's unacceptable to use it, because it makes so many wrong suggestions that it takes more time for the programmer, for me personally, I'm speaking from my own personal experience, it takes more time to understand the suggestion, to find the bugs in there, than I would write it myself. So then in most cases, I just ignore these suggestions. I use Copilot. So in most cases, I just ignore the suggestions unless there is something very simple suggestion, then I can accept it. And there is another product which is called AWS Code Whisperer, and you can read about it at the CTO of AWS, Mr. Vogels, on his blog. He has a pretty interesting interview with the developers of that, so take a look at that. And also there is a product called Tabnine. You can also check it. It was Codota before. Now it's called Tabnine, also in the same direction. So they are trying to use AI to help with the code completion. In my opinion, this direction is not very promising for practical programmers. It's more like it's fun, but not really useful for now. Second code companion which we use, it's pull request explanation. So I'm giving you an example here. So this is a pull request which was submitted to our repository. It was just a few days ago. And the part of the text which describes the pull request before the horizontal line, before the text called PR Codex Overview, it's written by the author of the pull request. The code below the line is automatically added by the machine learning, by the AI. So we connect, it's free actually, you can also use it. So I'll send you the slides later and all the links will be clickable here. So you can check PR Codex plugin for GitHub and you just connect it there, it's quite easy. And for free you get this description below the pull request original description. So AI looks at the files being changed, it looks at the description provided, it puts all these pieces together into probably a large vector and then gives this information to the machine, to the model, and the model generates this text at the bottom. The model suggests this PR adds support. So it's like a description which a real person would provide if we would ask this person, what do you think about this pull request? And it's very useful, to tell you the truth. We use this for the last, I think, maybe months or maybe a little bit more in our team, and we find it very useful because it helps me immediately understand what the pull request is about even before I take a look at the code. It just makes me a good explanation, and sometimes it helps find defects. It helps me find some problems if I see something wrong in this high-level description. If the AI misunderstand my code or misunderstand the code of my colleague programmer, then maybe I need to take a closer look at the details of the pull request. So this, I think, has a good future. This feature, it's pull request explanation. This is a code companion. Next one is for the reviewing changes. Again, and the same plugin. It's also PR Codex, which I highly recommend. And look how it works. It's in exactly the same pull request, which I just showed you. I posted the message /codex, and then I say, do you think this pull request is a risky one? And then it automatically, the robot, just look at my question, gives this question to the machine, to the large language model, to the probably ChatGPT they use behind the scene, and they give the description of the pull request, the code and the pull request all together. So they somehow compact this information into a vector. All machine learning technologies work like that, to my knowledge. So they somehow vectorize all the information they have. They put it to the machine, and the machine gives back the answer, again generating as this output is some kind of a combination of target attributes. So they create some sort of a large collection of input attributes, and here we get the target attributes, which turn into a text somehow. Again, there's a lot of magic happening there, but in the end, I'm getting the description, actually like a human being answering my question. It says blah, 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 it's hard to determine the level, but however, so it gives me more or less reasonable amount of reasoning, a good amount of information, which helps me decide whether this pull request can be merged immediately or I need to dive deeper and deeper and deeper. So this, I think, has a lot of future. I think this is where machine learning can be used and may be very effective as a companion for the programmer. It's a companion which doesn't write code for me, which I think in general is a wrong idea, to replace programmers by computers by writing the code instead of letting programmers write the code. So my personal belief is that programmers need to continue writing the code. But that kind of help is very useful when we ask the machine to look at our code and give an opinion about it. And here the machine, even if the machine makes a mistake here in this text, it's a forgivable mistake. I can forgive this mistake, comparing to, I can forgive this mistake much easier than I can forgive the mistake with the wrong code, which is suggested to me by Copilot, for example. When Copilot suggests me something and there is a bug in this code, I can't forgive that because it kind of it kind of moves me back into my, pushes me back in my coding stream. So I'm coding, I'm typing letter by letter, and then somebody just drops me a wrong piece of code into my file. So I need to analyze that and revert it back if I don't like it. So it's kind of annoying. But this is not annoying, even if the mistake is made. Even if the computer make a mistake, I can ignore it. I can just look at it and say, you just misunderstood what isn't there. But that's more or less okay, because it's not intrusive. It's just a recommendation, just a suggestion. It's just an advice which is coming from a robot. So if you can think in this direction, create robots like this one, because this one is really, it's really easy to create, having the ChatGPT on the background, of course. So the creators of this Codex plugin, they definitely didn't create the machine. They didn't create the model. They just connect to existing ChatGPTs through the API. But there are many other solutions similar to ChatGPT, or you can create your own one. So if you think in this direction of reviewing changes, of the reviews provided by the machine, then I think you can be very successful. You can create something quite successful. Next one, pull request risk analysis. Look at this list of pull requests, which I just copied from our repository just a few hours ago. Look at these badges provided here. The plugin is called CodeBall. So when the pull request is submitted to our backlog, then this CodeBall plugin just looks at the code and either attaches the badge approved, or the white one needs to be carefully reviewed. So there are a number of badges attached there automatically by the machine. The machine makes a subjective opinion about the code and either says approved, like it, it's good, let's do it, let's merge it, or it says no, please do the careful review. What's happening inside, if you look at the log of the logging information provided by this plugin, the plugin calculates the score. For the pull request, it returns a score from 0 to 1. And if the score is more than 0.9 or something, then it means that the code is good and it's time to approve it. If the score is less than 0.3, I believe, then they attach the badge which says, no, you need a careful review. If something between 0.3 and 0.9, then nothing is attached like in this pull request. You see, there is no opinion expressed by this robot. Very easy. Again, look at from the perspective of machine learning. So probably they take the code, they take the pull request details, they turn it into a large vector of numbers, and there's only one target attribute, which is a number, a single floating point number between 0 and 1. So the machine is somehow trained with some information coming from I don't know where, how they trained the model, I have no details, but in the end it's quite useful. If you can as well create something like that, I think many programmers will appreciate that and they can use it. Again, it's free. So I just connected it to my free open source repository and it starts provided. We just connected it a few weeks ago. So these tools are showing up on the market right as we speak. You can be one of those developers for similar products. Another one, Code Companion, is the plugin for VS Code. It's called Writer plugin by Mintlify company or a startup. So what it does, you just highlight, this is Rust. It's like a piece of my Rust code. So I just highlight the lines from 153 to line 165. And I click the button on the left. I say generate documentation. And the lines 146 to 152, the text in green is the Rust documentation, which is generated by the computer, by the model. So the model explained to me in the form of a documentation what is the method doing. And you look at the method, it's actually more or less accurate. So it somehow understood what is the body of the method, what it does, and wrote me the description in English. Again, it's a large language model is doing that. I think that on the background they have something like ChatGPT or maybe even ChatGPT or maybe something like that, which generates the documentation. Is it useful? I believe it is very useful. Because it's not only for writing documentation, but also for understanding what the method is doing. Let's say I'm taking an existing piece of code or existing library from somebody who didn't care about the quality enough so to write the documentation. But I want to understand what's going on there. So instead of looking through the code myself and trying to figure it out, I just highlight the piece of the code, I click generate documentation, and I get the full description of the code. Isn't it nice? I think it is, and I think that's again something for the future, something which programmers may need in the future, and you can think about making something like that for the analysis. And you know what I think you can combine, that's something which definitely need to mention, that I think the real future, not the real, the closest future in the area of program analysis using machine learning is in the interaction between machine learning methods, which are purely non-deterministic, which are based on the, like I said, the black box model, which makes decision of we don't know how, and deterministic methods. So we can combine them. So we can look at this code here in this block, make a control flow graph, apply data flow algorithm, maybe apply symbolic execution, and then go to a large language model and ask the model what it thinks, and then combine these two answers. So we have a deterministic answer using the methods which we know already, which are traditional, which are coming from the program analysis, 30 years of research, and we take the new things which are non-deterministic, which we don't know how they work, they just tell us something. They just print the text, which is sometimes contains mistakes, sometimes we don't even know what it contains. But if we combine these two methods, deterministic methods and non-deterministic, we potentially, I believe, can receive really bright results. And this is not happening yet. So this is probably the future. You can be part of that future if you, like I said, combine data flow analysis, for example, with machine learning somehow. Then you can outperform many of the existing data flow analyzers or maybe compilers or maybe these tools which generate the documentation. So this is explainers. Explain these to me means look at the code and explain me what's there. Next, Code Companion is it gives all in one package. I found it's called Safurai. It gives a few of the things which we discussed and maybe and also will discuss in one package. So you highlight this code. So you see on the right, it's VS Code plugin. So I highlight the piece of the code. Again, it's in Rust. You see there is code which does some cycle. In the cycle, there are some manipulations with the data, with the numbers. So it's not exactly clear what's going on there. Even the code is quite short. Then there are a number of buttons on the left. So you see there are buttons. One it says explain. It will probably do the same which I just showed you before. Another one is refactors. If you click refactor, it will just rewrite the code a little bit. It will make it maybe faster, not maybe faster, but somehow maybe better looking or something like that. You can generate documentation, you can optimize, you can find problems, you can unit test, you can even generate unit tests. So a number of features, some of which we will discuss in a minute, some of them we just discussed. So it's all in one package, Code Companion, unfortunately only for VS Code right now. But I think it's worth taking a look at this Safurai solution, which they definitely will, looks like they will implement for other IDEs, and it could be interesting potential future use case scenario when I just know that there's one panel on the left. I just highlight the piece of code, click one of those buttons, and get the magic, and the code gets improved, refactored, explained, optimized, and something like that. Next, here I don't have a picture. I will just tell you just verbally how I think it should work, and unfortunately I don't have it right now. I only found that there is a solution in IntelliCode, part of the Visual Code Studio, which I don't use, and which is only for Windows platform, as far as I understand. So something which I didn't touch myself, but that would be great to have. Repeat after me what it means. When you write the code, sometimes it happens when you need to do certain changes to different pieces of the code base repeatedly. For example, you switch from one version of the library to another version of the library. And everywhere in your code, the way you use this library has to be a little bit changed. Like 2 lines need to be replaced with 1 line, and depending on the context, you cannot do it just with the find and replace feature. With the regular expression, it's not going to happen because the changes are a bit more complex than just changing regular expression. So you need to go through these sometimes dozens or maybe hundreds of files and just manually change those a few lines, from 2 lines to 1, from 2 lines to 1, and you go and you do it again and again. So I believe it would be nice, and this actually the blog post explains how it works. Would be nice if some machine, some model which stays in the IDE, just learn what I'm doing, just see my actions, see that I'm doing the same operations again and again with some variations inside. So I'm not doing exactly the same operations, like with the examples of this good morning, good afternoon, good evening, and good night. We're not exactly the same time is coming in. So the time changes, but the actual output is the same. So the time is 8 o'clock or 9 o'clock or 8:30 or 9:30, the answer is the same. It's good morning. The same here. So what's coming in the input could be a little bit different, but in the output I do the changes which are the same. So it would be great, imagine in the IDE I just go make one change, another change, and then on the step number 3, the IDE will just pop up and say, hey, I understand what you're doing. You're just changing these 2 lines to this one, and I learned already from your actions that I can apply those changes to other 100 files. That would be amazing. I hit this problem quite often. It would be great if the IDE would support it. Right now, it doesn't. So that's definitely something for the future for the machine learning companions. Another one example, again, I cannot show you the picture, but it's interesting something which I didn't use myself, and I tried to, in order to make the illustration. I found this Ponycode platform, which last year was alive, but now it's unfortunately not. I didn't manage to find how it works to try it. But the idea is simple. We discussed that on the lecture before, when we discussed symbolic execution. We discussed test case generation. So when you look at the code and you generate the test case, or maybe a number of test case, which will find, using symbolic execution, which will find the input parameters for the code in order to ensure higher test coverage. You can do the same with machine learning. You can do even better using non-deterministic methods. So symbolic execution will give you one result, one output, one coverage, test coverage. They claim, and not only Ponycode, but a number of research papers, they claim that it's possible to do it with machine learning with even higher coverage of the code, even better. So symbolic execution, this concolic testing, which we discussed, they will give you certain coverage improvement. They will cover your code with more tests, which you cannot write manually, which will take you more time than they can generate, than they can spend. So they claim that machine learning could be even even better step forward to generate the test cases using non-deterministic methods. How exactly it works, I leave that topic for you for your research by yourself. Like I'm saying, I didn't manage to try it. If I would try it, I would show you the example and explain how it works. But I can't find a really working product which I can download, give my Java code to it, click generate test, and I just get the test. So if you find out one, try to use it, or maybe try to create your own one. Next one, and this is one of my favorites, automated refactoring. I found this picture on the CodeScene website. It's the platform which they promise they do something like that. But look at the picture, look at the idea, which I think is really interesting. It has a huge future. The idea is that you know what is refactoring. Refactoring is changing the code in certain way such that the code continues to behave like it was before, but it looks different. Maybe it works faster. Maybe it just looks more nice for it's more understandable for the user. For example, a simple refactoring, you say x equals to x plus 1. you know what code is doing. The code just increments the variable x. Imagine we ask the computer to refactor that, and it replaces the line x equals to x plus 1. It says x plus equals 1, or maybe x plus plus in case of C++. So instead of having the long line where you say x equals x plus 1, we just say x plus plus. This is refactoring. We didn't change the behavior of the code. It works exactly the same. The compiler takes it and turns into the same instructions for the machine. But for the user, maybe x plus plus looks better than x equals to x plus 1. And there could be many such refactorings which can be applied to the source code. There are books written about that, how you can refactor the code, how you can look at some refactorings are smaller, like I just gave you an example of the one where you place just one line, make it a little bit shorter. Some refactoring could be large. For example, you take a large method, a large function, and then you break it down into two functions. So you find in this large function, you find a piece which you can take away and then call it from the original function to that one. What it's for? To increase the readability of the code. So the code will be more readable because now there's instead of a large function, we have two functions and each of them is smaller. So instead of 100 lines in one function, you have 50 and 50. That's called automated method extraction. And there could be many other refactorings like that. There could be hundreds of them. And there not could be, but there are hundreds of refactorings, which people know already. People studied them for decades, and we know how to apply them. But we cannot take the source code, written by me, for example, give it to the machine, and the machine will apply all 200 known refactorings. If it's going to happen, then the code which I'll take back from the machine will look completely unfamiliar for me. I will not understand what happened. I will not understand the code which is returned to me. The changes will be massive and unacceptable by the majority of real use cases. So we cannot just build the machine which will refactor automatically the Java code by applying all known 200 refactorings to it. For the reasons I just gave you, because the result of this refactoring will be unacceptable by programmers. Programmers will just reject that, will say, you ruin my code. Well, maybe you make it better. Maybe you make it look better, or maybe even work faster, but it's not my code anymore. I'm not going to accept that. If you send the pull request with so many changes, it will be rejected. The question is, another extreme, let's say we take the code and we apply just one refactoring, and then give it to programmers. In this case, the changes will be minimal because some refactorings are not applicable to the specific code. So we will be providing minor refactoring changes to programmers, and they will also reject that. They will also say, like, you're annoying me too much with your changes. If, let's say, we create a machine learning driven robot which takes your code from your repository, look at the code, and make a small micro refactoring, one of those 200 refactorings, and submit the pull request. And do it every day. It will be annoying for programmers because the amount of changes will be very small inside each pull request. And programmers will just shut down this robot and say, you're not giving any real value to us. You're just making really small micro refactorings which don't change too much. So how do we find a balance between one single refactoring and 200 refactorings being applied at the same time? So there should be some middle line where we say this is the right amount of refactorings to apply to the code. So we decide, we choose them and say, let's say we build a robot which takes your source code on Java, 1,000 lines of code, and it somehow decides that these 15 refactorings is the right amount to apply for this code and send you back as a pull request. And there is a highest chance for you to accept this pull request. So somehow we can't build such a machine. We don't have it right now. I mean, these code scene guys, they seem to have something in this direction, but I'm not sure. You can try it yourself. I didn't manage to make a real case. But they say it right. Look, they take a look at the code health improvements. So they have a collection of code health improvements, and then they classified helpful diffs. So they apply all possible improvements at the same time. So they take your Java code, they apply 200 improvements, and they receive 200 classified helpful diffs. And then finally, the final step, they decide, they rank them somehow, and they provide ranked refactoring recommendations. So they somehow say, you know what, we know what's going to happen if we apply 200 different improvements. But the improvement number 7 and improvement number 15, these are the two improvements which we rank the most important right now. And these two we submit to programmers. This decision cannot be made deterministically. We need artificial intelligence to make this decision, because I don't know how to write such a program in a deterministic way. It's better to somehow to train the machine so that the machine actually makes this decision. Which of these recommendations should go first? So this, I think, the future of really, very strong and massive impact that could be made by artificial intelligence to the coding. And the final funny example for you, again, ChatGPT, like we all love. So take a look at this. Question which I posted to ChatGPT. I said, please look at this code, which is written in a language which ChatGPT doesn't know. It's not Java. It's our own language, our own programming language. I'm sure you would also not be able to understand what exactly it means unless you know our language, unless you have some experience with it. So I gave this to ChatGPT and I said, what do you think about it? So what do you think in terms of quality, readability? Do you see any issues there? And I can explain you what the code is doing. So this is the definition of an object. So object is called f. The object has one argument to be encapsulated, which is called x. And then the implementation of the object is if x is less than 2, then return x plus 25. Else return x plus 25. So there is an obvious duplication, obvious redundancy in this code, because in either case you return x plus 25. Either x is less than 2 or x is more than 2, it's going to be x plus 25 returned. So the code definitely has some issues with the optimality and the potential readability. So this is what ChatGPT told me. ChatGPT said, based on the code, and it started to, it really tried to understand the code. It didn't give me the right answer. You can read it. You can read what it says. It says, in terms of readability, there are some aspects of the code could be improved. So first it looked at it and don't say this symbol, use function instead. So it's trying to, it understands that it is some sort of a function. It doesn't understand it's an object, but it says it's a function. So instead of that, please use the keyword function. So it tries to improve, change the language, change the design of the language. Then it says maybe confusing for somebody who is not familiar. It's not immediately clear. So it criticizes the design of the language again. It doesn't understand what these things mean, but it just suggests that its readability is not as perfect as it could be. Then it says something about indentation, that again, it's hard to see what is what. And finally, it gives me the suggestion how this code can be improved. Again, the suggestion is wrong. It doesn't make any sense. Actually, you see, it says that the JavaScript here, even though it knows it's not JavaScript, and it suggests how to rewrite it to change the syntax of the language. My point here is that it actually sort of thinks. So it is some intelligence in there, for sure. Whether it's a intelligence which is close to human intelligence, or it's still very immature and very primitive intelligence, but it's definitely intelligence. So it reasons about the code, and the question for us is how can we use this intelligence for practical applications. And I gave you a number of examples so far how we can use these artificial thinkers to let them reason about our code. My belief is that, I'm kind of finishing, so my belief is that directly using this intelligence for helping us write code, it's a wrong idea. So I don't think these ChatGPT or similar systems in the reasonable amount of time going forward will be able to actually write code for us and actually do like it is promoted, like it is advertised right now, that programmers will be fired and this GPT or AI systems, they will be just writing the code. I don't think it's going to happen because they're quite stupid and they're quite limited. Their intelligence is very limited. But if on top of these machines, if on top of this artificial intelligence, you can build a next layer which will take the real problem from the source code and formulate the proper so-called prompt for the machine, formulate the request and send the request to the machine, and then interpret the response properly, and then convert that response into the relevant business piece of information. For example, like I said, the analysis of the quality of a pull request or the analysis of the documentation of the code, something like that. Then it's going to be a very useful instrument for programmers. So the direct usage of ChatGPT will give you something very funny, very interesting, like in this example, but absolutely not useful. Because if you look at this more close, it's garbage. I mean, the way it interprets information, the way it tries to give me some useful answer is absolutely unuseful. It's only for fun. But the previous examples, they show you that it's not for fun, that is really actual practical application of that. Okay, we have 5 minutes left, and I will show you what I think will be far future, what's going to be of the program analysis, and then we finish the lecture and we finish the course. So what's next? I think I will give you three points, three directions which are, in my opinion, the future. The first one, you can read the paper which was published just about a year ago in Communications of the ACM about neural software analysis. So I'm not going to repeat the content of that, but the idea overall sounds like by designing the tools which look at the code and analyze control flow graphs, data flow graphs, symbolic execution analysis, everything we studied on this course is just the first generation of analysis, the first level. We can go on the second level if we start analyzing the people who write the code. Their processes in their brains that happen when people write the code. So we combine the analysis of the code with the analysis of coders. Not only deterministically looking, or maybe even non-deterministically looking at the code and ignoring the authorship of this code, but we'll look as a combination. We'll look at this ecosystem as in a combination. We'll look at the code and the coders. I think this is what they mean by neural software analysis. So we see how the brains of people, work when they write the code. And the second paper is more or less in the same direction. So I said I'm giving you three directions. I'm giving you one direction. The second one, people also not really not so long time ago, they published a paper about understanding. It's one of the I think the year is 2014 or 15. I didn't write the year here. I think it's 16 or 15. So they suggest it's one of the papers. There were, after that there were other papers. So they suggest to put the sensors on the human brain, on the brain of the programmer, and see how the brains behave when programmers write the code. So what happens when you do refactoring? What happens when you read the code? What happens when you hit the bug in the code? What happens when you debug the code? And then by looking at this information, maybe we can invent new mechanisms of reasoning about the code. If we know who was writing the code and what that person was thinking at this moment. So we're not looking only at the control flow graph. We look at the control flow graph together with the person who wrote that graph. Who was that person? How old was that person? In what mood that person was at the moment of writing the code? And what usually this person is writing? What are the mistake? What are the most typical mistakes that user is doing when, or what are the group of people who this person belongs to? What is the most typical set of mistakes these people are doing? So many things which we can study if we let ourselves jump from, escape from the territory of determinism of control flow graphs to the territory of more social and more behavioral analysis of the coding, of the process of writing code. So to summarize, I would say that we need to start thinking about programmers as parts of the programs. So usually everything we studied on this course, we were looking at programs. We were looking just at something which is already written by programmers, and we take it away, we forget about who wrote that, we just look at the code. The compiler doesn't care who wrote the code. The compiler just take the code, compile it, and put the analyzer just take the code, analyze it, and makes the decision. But they ignore the authorship. They ignore who brought the code to us. What was the intent of the programmer? What was, like I said, what was the mood of the programmer? What was the experience of the programmer? What this programmer, I don't know, how much money this programmer is getting. Maybe this also affects the quality of the program. So all of that we can start taking into consideration, and that will open a new domain of research, a new set of potentially very powerful instruments, which we don't even see right now. Right now we see IDEs which were created 30 years ago. So the idea of a text editor and the idea of IDE, which helps us to write the code, it is 30 or maybe 40 years old. It was there when you were not even born. Maybe even I was not even born. Already we had that editors which help us edit the program and help us move the text left and right and make the changes and everything. Now we're standing right at the edge of a new era of programming, where we programmers will become part of the programs. So you may start thinking about this. I think it may open a lot of opportunities for you as researchers, as future researchers, and if you don't want to be researchers, think of you as a programmers. So be prepared for these new tools to start using them. So try them. Some of the tools I showed you today, try to install them, try to use them in your projects, and always look for new. They show up every week. Some of the tools which I showed you, they were 1 month ago, they were not in the market. Now they are. Look, scan the market, scan the what's happening on the GitHub, what's happening in the IDEs which you use, install those plugins, and see how they can start helping you, how they can start turning you into a programmer of the next generation, who is not only a programmer who writes the program, completely being detached from the program, but who is a part of a program. So that's it. Thanks for being at this course. I hope I motivated you for some future research. Maybe see you sometime in some of the projects. Happy coding.